is Becca.
Mi nombre es Pablo.
My name's Sam.
Thanks for watching us on DPS TV. Hi, today we are going to talk about imaginary numbers, and very specifically we're going to talk about powers of I, or powers of imaginary numbers. We'll get to a little bit more on imaginary numbers later, so this is just part one. Let's talk a little bit about what imaginary numbers are and where they came from, and then we'll get into what they are and what they can be used for and one use for them. So imaginary numbers, go ahead and cut to my screen. Imaginary numbers, they were invented by an Italian mathematician. His name was Bombelli, about 500 years ago. And the way that imaginary numbers came about is that kind of the way that any number comes about is that there's a need for them. Think about when you were in elementary school and you were just learning division and you learned that 10 divided by 2 is 5. But then you came across a problem like 8 divided by 3, and maybe at first you said 8 couldn't be divided by 3, but then you learned about a type of number called decimals or fractions. So imaginary numbers come from when a number, we try to square root a negative number. And if you don't know about imaginary numbers already, you may say that you cannot square root a negative number, which may be true, but we actually can. We can square root a negative number and get an imaginary number. And let me explain. So Bombelli was actually, when he came up with imaginary numbers, he was working and trying to solve a quadratic equation. So something like this: x squared equals -1, maybe something like that. I don't think this was the actual equation he was using. But when he tried to solve it, he got stuck because we said, oh, we can't square root a negative number. Well, what he did is he created a solution for a problem like this. I think it was actually a cubic function for a problem like this, and he worked his way backwards, and it ended up working, which is why they're called imaginary numbers, is because he started with something that was made up, and it ended up making it work in an actual math problem. So imaginary numbers are a type of number, even though the name kind of insinuates that they are not a type of number. They are types of numbers. So this is our set of real numbers here in the blue, and that includes all types of numbers that you've worked with before, like rational numbers, which are fractions and decimals, integers, which are positive and negative whole numbers and natural numbers, and also even the set of irrational numbers like pi or some square roots. Imaginary numbers doesn't fall under any set of real numbers. They're kind of a subset on the side. And then we also have what are called complex numbers, which we'll talk about in a later video of how to work with complex numbers. So imaginary numbers, and you might see here, they are all based off of the idea of a negative square root. The big idea is that I, or the most basic imaginary number there is equal to the square root of -1, always. Now, from there, you can kind of, so that part was what was invented. From there, you can kind of discover different properties that imaginary numbers have. So for example, let's just say I took my I, which is square root of -1, and I squared that. Now, fundamental rules of algebra, what I do to one side of the equation, I have to do to the other. So we're going to square the other side of the equation as well. So what happens then, you may notice this already, is that this square root and square, they're opposites of each other. They're inverses, and so they cancel each other out. So what ends up happening is that we end up rewriting our equation and saying that I squared is equal to -1, which is a real number. So if I take two imaginary numbers, multiply them together, I get a real number. Kind of like the same idea that if I multiply two negatives, I get a positive. It's a very similar idea. So I squared is equal to -1. We're going to continue this pattern and just see what happens. So let's say I were to do I cubed. What does that equal? Well, you can think of I cubed as the same thing as I squared times I. And I squared, well, we already proved up here that I squared is equal to negative 1. So I squared times I is equal to negative 1 times I, which just simplifies to negative I. So we can say that I cubed actually simplifies to negative I, which is very interesting. So continuing this, and I have a point to this, I promise. Continuing this, let's look at I to the 4th power. Think of I to the 4th power as I squared times I squared. And again, we saw earlier that I squared is equal to negative 1, so I could replace I squared with negative 1. And that means that I have negative 1 times negative 1, which gives me positive 1. So that then means that I to the 4th power is equal to positive 1. Now I'm going to keep going one further, and then hopefully we can see some patterns here. Let's look at I to the 5th power. Think of I to the 5th power as, well, we could do I to the 4th power times I. And we already know from up here that I to the 4th power is just equal to 1. So that means that this is equal to 1 times I, which just equals I. So I to the 5th power actually just simplifies to I. So what's kind of happening here, and I'm going to point your attention to this powers of I circle that I have here, is that I to the 1st, of course, simplifies to I. I to the 2nd, we saw, simplifies to negative 1. I to the 3rd is negative I to the 4th is 1, but then it starts repeating itself. I to the 5th simplifies just to I to the 6th is going to simplify to negative 1, I to the 7th to negative I to the 8th to 1, and so on. And this circle and this cycle kind of repeats itself. So the other thing that you may notice is that every one of these powers of I that simplify to 1 is going to be a multiple of 4. So for example, I to the 4th, I to the 8th, I to the 12th, I to the 16th. These will all simplify to 1. So that being said, we can, with these patterns and knowing these patterns in mind, we can simplify any power of I, and we want to, because a power of I is not simplified unless it is simplified to one of these 4 answers. So we can simplify a power of I by dividing by 4, dividing that power by 4, because every power of 4 is just going to equal to 1, and 1 times anything is just itself, doesn't change anything. So then what happens is, if I were to think of this as, all right, take this power of 13, I divide this by 4. 13 divided by 4 is going to give me 3 with a remainder of 1. There's going to be 1 left over. So that means I'm going to have 3 I powers of 4 with a remainder of 1 left over. And so all of these I to the 4th power just equal 1. 1 times 1 times 1 times I. They don't really matter in the scheme of, in terms of simplifying. So this is going to just simplify to I. So going to kind of a general rule, if our remainder is 1, our answer is going to simplify to I. If my remainder or my leftover is 1, and you can kind of see that right here. My leftover is 1. If my remainder is 2, then I will be left with I squared, which means we'll simplify to negative 1. If my remainder is 3, then we're going to be simplifying to I to the 3rd power, which we see up here, is simplifying to negative I. So if you can find the remainder after you divide by 4, you can figure out which one of these 4 imaginary or non-imaginary, I guess, which one of these 4 solutions it simplifies to. So let's try a couple more. So I have I to the 25th power. If I take 25 and divide it by 4, I end up getting 6 with a remainder of 1. Because 6 times 4 is 24, there's 1 left over. So that remainder of 1 is doing very similarly to what the first problem did. It's telling me that I'm going to be simplifying to a remainder, or to I, just I. We'll do I to the 40th. Same deal, we're going to take 40 divided by 4. I end up getting 10 with no remainder. So that's like this one. So that means this just simplifies to 1. Last one, you kind of get the point at this point, is we're going to divide by 4. I end up getting 3 because 3 times 4 is 12 with 3 left over. So remainder of 3. So that means if my remainder is 3, my answer is going to be negative I. So this is just going to simplify to negative I. So first rule, I guess, just to summarize, first rule in working with imaginary numbers is that if we have powers of I, they are not simplified. We have to simplify them, and when we simplify them to one of these 4 answers. And you can simply do that by dividing your exponent by 4 and looking for the remainder. And that is how we work with I, or imaginary numbers. We'll talk a little bit more about how to work with them later on. Oh, I did want to say this is a very, very common SAT or ACT question. You almost see this on every ACT or SAT, is some sort of simplifying imaginary numbers. And if you just know this little portion right here, you'll be totally fine with it. So hopefully that helps and is a good introduction to imaginary numbers. And like I said, we'll talk a little bit more about imaginary numbers later on and how to work with them and how they're useful. Thanks for watching this episode of Tutor This. As always, if you have questions or suggestions for future episodes, leave them in the comments below. Remember to click the like button below, and if you enjoyed this video and want to see more like it, hit subscribe.